Hey everybody, welcome to Chapter 4 on Central Tendency. We are starting our first foray into descriptive statistics, which you'll remember is just ways of summarizing data, typically ways of summarizing sample data. So, I know that you are thinking, all right, central tendency, it's mean, median, and mode. We learned that in middle school or earlier for some of you, but this is a nice refresher and it also ties in with a lot of other material that we've been talking about so far this semester. So let's dive in. But first, let's get some review in. All right, let's pretend that this is a graph of a sample of Americans, and on the y-axis you see its frequency. On the x-axis, let's say it's the number of times they've had Indian food in a year. Now, the question is, what type of skew are we seeing in this particular distribution? This is called a negative skew, or sometimes called a left skew. And you can tell that because there's sort of a tail that goes downward and to the left. As always, we've got some learning objectives for this chapter. So first of all, we're going to see what we can learn about distributions from measures of central tendency. We'll learn how mean, median, and mode are used as measures of central tendency, and also how they compare in different types of distributions, whether they're skewed or symmetrical. And finally, we'll talk about which measures of central tendency to use when you're actually describing particular distributions, which one's going to be the most preferred for that type of distribution. I really like this flow chart because it shows us the different kinds of descriptive statistics that we'll be talking about over the next couple of chapters. The first one, of course, being central tendency, so that's mean, median, and mode. Then we're going to be moving on next chapter to talk about variability, or the spread. That's differences between scores in a distribution. And you can also think about other kinds of descriptive statistics like the skew of a distribution, or just the shape of the distribution of numbers. You can talk about frequency. You can talk about percentages, right? All of those things are just ways of describing data. As good scientists do, we have to begin with our definitions, right? So what is central tendency and what are the measures of central tendency? So a measure of central tendency from the book says it's a statistic that represents the typical score in a distribution. And it really is just a way to summarize an entire variable's distribution into a single value. And remember, when we use the term distribution, we're just talking about a set of numbers. Typically, we're talking about the set of numbers for a particular variable that you're measuring in your sample. Maybe it's extroversion, and so the distribution is going to be all of the extroversion scores for each of the people in your sample. So let's jump in and first learn what we can know about a distribution from measures of central tendency. Something that's really nice about measures of central tendency, like mean or median, is that they give you kind of an overall sense for what's going on. And sometimes they are really well representative of the data, and sometimes they're not. What you're looking at here is just a graph of average monthly precipitation, which are those bars, as well as average monthly temperatures, with the highs being the red line and the lows being the blue line. And so this is showing you tons and tons of information, and it's a really useful way to illustrate this kind of data. If we looked at just, for instance, maybe the amount of rain that fell in April, which looks like about 4.5 inches, well, some days in April it's gonna rain not at all, and some days it's gonna rain 7 inches, and some days it's gonna rain 2.3 inches, right? And so we aren't really sure by looking at this graph if that number 4.5 inches as an average is really representative of April's rainfall as a whole, but it is nice that we can summarize that into one single bar, right? We can also ask about central tendency in terms of income, and this is kind of interesting. Most people, most statisticians or people who work with data related to income tend to prefer using the median as the measure of central tendency as opposed to the mean or the average, because a lot of times there are really severe outliers, because just a few people in any given population will make a lot of money, right? Like, the people who own companies or something like that. Whereas most people make sort of like, I don't know, like a medium amount of money or an average amount of money, right? Somewhere between like 30,000 and let's say $100,000 a year. But then there's always going to be a couple people who make several $100 million. And what happens is for those outliers, it really pulls the average out from the main pack of the data. And that can give us kind of a false sense of what the mean would actually be. Median isn't as affected by those outliers, and we'll see that on the next slide. So what we have here is annual household income. There's two lines. The colorful one is what Missouri residents make, or Columbia, Missouri residents make, and the black line is actually the national average. So you can see that there's kind of a lot of people who make like between, let's say, 20 and $60,000 a year, because if you look on the y-axis, which is talking about percentage of households, those are really high percentages in the four, around 4% or something like that. And then if you look towards the right end of the graph, well, it starts to really go down a lot, right? When you're talking about people who make 400 or 500 or $600,000 a year, there's very, very few people who make that amount of money. And so I put a red line here that indicates where the median household annual income is. It's about $63,000 or $63,580. And let's compare this to how the average annual household income looks. You can see that the average annual household income is $83,000 a year. But the problem is that the mean, you can see where that dashed line is. It's not even really associated with the largest frequencies in this graph, meaning those, in the kind of 20 to 50 or 20 to $60,000 range. It's way to the right of those things, right? So that means that it might not actually be as representative of the typical household income. And that's because it's getting pulled out to the right by those outliers. So actually median better represents this data because it's more in line with like those higher percentages, those kind of higher mountains or peaks, if you will, in the distribution. All right, now let's talk about how mean, median, and mode are used as measures of central tendency in statistics. And again, just to summarize, central tendency is a measure of the typical score in a distribution. And so when I say typical, that usually means that the higher frequency, meaning like the higher the bars or the taller the mountain peak is, well, the measure of central tendency that you're choosing should be somewhere around that, because that measures the typical score. That's where most people in the distribution are bunched up, right? And so it's just a way to summarize all of the distribution into a single score. And to define a little bit each of those measures of central tendency in turn, as you all know, the mean is the average score in a set of data. The median is the middle score in a distribution. If you align the distribution from lowest to highest in terms of the number of whatever variable scale you're using, the middle score such that half the scores are above it and half the scores are below it. And then the mode is just the most common score in a distribution, which means it will always be wherever the highest peak is, that's what the mode is, because that means that that's the most frequent, because the y-axis is always frequency, right, or percentage. And so the mode is going to always be the exact highest peak. It can also be multimodal, which we'll talk about in a second. So first up, let's talk about the mean. And of course, this little Taylor Swift meme here is my attempt at staying relevant. But as you all know, how to calculate an average or a mean for any given set of scores for any distribution of a single variable, you just take the sum of all of the scores from all of your participants, and you divide it by either how many participants there are in the case of a between subjects design, where people are only taking the measure one time, or maybe you divide it by the number of measurements, because sometimes there'll be one group of people taking a certain measurement many times, like doing a personality test 6 times over the course of a month or something like that. And you have to find a way to summarize that. The mean is by far the most common measure of central tendency used in research and in psychology. And as you know, it uses all the scores in the distribution in its calculation. You can think of it as kind of the balancing point of the distribution, if that's a useful visual for you. And we'll see a little bit more what I mean by that in a second. So as I was alluding to in our discussion of income distributions, outliers, which are extremely high values or extremely low values in any given distribution, they will really kind of mess up the average because they really highly influence it and pull it in either direction in the distribution. And so when you have outliers in your data, what psychologists will do, well, they'll establish cutoffs before they actually collect data of, like, if outliers are beyond 2 standard deviations, and I'll talk about what that means next chapter in variability, then you can just delete those outliers or not use them in your calculations, and that's totally cool to do. And it basically helps you be able to use mean as your measure of central tendency. So again, what this outlier is going to do, and in the upper graph, we see that there's an outlier on to the right of that graph. Somebody has accidentally put in their age as 356, right? Which they probably meant to say 35 or 36, but somebody accidentally put in and entered into this distribution of age that their age was 356, and that's going to take the mean age and pull it way to the right. And so instead of, the mean should have been maybe around like 35 or something like that, now it might be something like 39 or 45, and it gets really pulled out. And these two graphs below show that when you have skewed data of any kind, the mean is always going to be pulled further to that tail, meaning the mean will be pulled to the left in a negative skew, and the mean will be pulled to the right in a positive skew, whereas the median isn't pulled so far, and the mode still stays exactly where the highest frequency is going to be. And a very cool thing about symmetrical distributions is that the mean, median, and mode are all the same number. That's pretty handy because the mean doesn't get pulled out by any of the outliers because it's pulled evenly in both directions, which means it doesn't actually move at all. So that's a nice thing about symmetrical distributions, and we'll talk more about that later on. All right, so in statistics, we use a lot of symbols, and it's important to be able to identify these symbols and know what they mean. The first one is just X, and it could be lowercase x, sometimes it's uppercase X, but it represents a raw score. And a raw score would just be like if somebody self-reports that their age is 39, that's one raw score from one participant. If a researcher conducts a cognitive memory exam on a participant and they get a score of, I'm just going to say 7, it's just kind of a random number, that's one single raw score. And so X would equal 7 for that participant. But the sample mean, represented by what we call X bar, is an average of all of the raw scores for one particular variable. The population mean, though, is represented by the Greek symbol for mu, and that can get a little confusing. When we make hypotheses, we're talking about populations, but when we actually conduct data analysis, we're talking about samples. So we'll talk more about that. But sum is represented by this, what looks like kind of a capital E maybe. It's called sigma, and that means if you have that symbol in front of a bunch of numbers, you add all those numbers together. Sample size is represented by lowercase n, whereas population size is represented by uppercase capital N. So to use the language of statistics and incorporate these symbols when we're talking about calculating the mean, mean is x bar and it equals sigma x, meaning the sum of all raw scores, the sum of all raw scores, divided by the sample size, divided by how many people are in your sample. Okay, and for a little bit of review, if we're talking about a number that describes a sample, that is the sample mean, that is an example of a statistic, right? Any number that describes a sample is a statistic. If we were talking about calculating a population mean, which you can't actually know, we're always going to estimate based on the sample mean. But if you were trying to figure out what a population mean is, it would be mu, which is the population mean, equals the sum of all scores in a population over the size of the population, which is capital N. Now, I just said we never know the population mean, mu, which isn't quite true. There's specific situations where we do know it, but typically, as we've mentioned in class, we use sample data to estimate population data, meaning we use the sample mean to estimate the population mean. Once in a while, though, we actually do get an entire population mean, and we'll talk about that later. All right, let's get a little practice. Find the mean of these raw scores: 1.20, 4.31, 2.67, and 5.45. So in order to find the answer, you add up each of those four scores, divide by 4, and you should get 3.4075. But remember, in this class, we're going to round basically everything except for p-values. We're going to round everything to 2 decimal places. So that would be 3.41. All right, that's where we're going to leave it off for now. I'll see you in the next one.